Hi everyone, my name is Kate Goldenring and this is Sudesh Girdhar, and today we're going to be talking about breaking the latency barrier, tackling compute and network delay with globally distributed WebAssembly functions. Just a little bit about us to start. I am a software engineer at Fermyon, where we do everything serverless WebAssembly, and I've been lucky to start my career in the open source space, working on CNCF projects such as Akamai and Spin. And for several years served as co-chair of the CNCF IoT Edge working group. Since then, I've moved more to the WebAssembly space and work on documentation upstream there to make sure everyone has a good first start with the WebAssembly experience. And then outside of the workspace, I'm an avid mountaineer and love to help other people get to the top of mountains with my local mountaineering club in Seattle.
Thanks, and I'm Sudesh Girdhar, go-to-market solutions for commerce, travel, and manufacturing. I work for Akamai. I've got 10 years of deploying master of edge infrastructure, crafting full-stack solutions. You may recognize me from some of the stuff that I've worked on in the past, which includes some Kubernetes, OpenShift, and Cloud Foundry, and the Spring Framework. Also, a couple of other projects like Panamax and image layers, where I provided go-to-market support overall. So I get to go deal with how do we deploy this to our customers. I'm really fanatical about scaling performance and making front-end systems hum. And if you don't see me in Atlanta, where I'm based, you might find me traveling around the world. Love to go on epic adventures. And if you're around, find me for a bicycle ride. Yeah. Let's start with a challenge that's been haunting cloud applications for years, latency. If your function takes longer to start than it takes to blink, you've already lost your user. Every 100 milliseconds of delay costs engagements. We see users bounce. We see carts abandoned. We see streams stutter. And we've all had this experience in the real world. Serverless was supposed to help us build faster, cheaper, and easier, and it did, but it didn't fix latency. Cold starts over 200 milliseconds, regional confinement, and vendor lock-in have created a new kind of wall, the latency wall. Now, the answer isn't another cloud region or a bigger instance, it's proximity. So even if you're optimizing your code, you can't outrun geography. That 400 milliseconds bar that you see up there, that's the round trip from the other side of the continent. We're shrinking it down with this example to single digits. Here's what's really going on. With a traditional serverless platform, Lambda, Azure functions, you get two components, network and compute time. Compute time is what Fermyon helps crush with WebAssembly functions that start in sub-milliseconds. But the other piece, network time, it's just plain physics. When your users are 3,000 miles from your function, even a small function takes a long time. So we've solved elasticity, and now we're solving proximity. Most serverless functions weren't built for real-time UX. We see three constraints: high latency, strict limits, and vendor lock-in. So what that means is that all of these kind of contribute to the time it takes. Edge functions flip that instant on, sub-millisecond start, flexible and scalable, can run complex and longer logic, open and portable when built with open source, and run from Kubernetes to the edge. The answer to latency isn't a bigger region, it's proximity and a faster runtime. Now, this slide has a lot of data on it, but let's compare three worlds of serverless. At the top, you're going to see kind of the traditional functions, which include Lambda, Azure, and GCF. Start up in 200 milliseconds plus, usually single region only, and most are locked to a specific cloud instance. Whereas in the middle, we've got edge functions from Cloudflare and Fastly, global and fast, sub 5 millisecond cold starts, but they're still very proprietary. You're renting performance and not owning your portability. And then here at the bottom, edge functions, Fermyon edge functions. That's our open source built on Spin, sub 1 millisecond startup, 7 languages, no cloud lock-in to deploy. Now, everything we've talked about, low latency, open source portability, instant startup, exists right here as a live platform. Fermyon and Wasm functions run inside Akamai's global network, tied directly into our compute in Linode. To show you what this actually feels like in practice, Kate's going to walk us through.
Thanks, Sudesh. So we've mentioned Wasm a lot. If you saw that grid that Sudesh showed you earlier, we saw how those Legacy serverless functions use different isolation mechanisms. They use micro VMs or containers, which are slow to start up. So cloud providers have had workarounds of having pre-warmed instances and so on, which adds to your expenses as a user. So we wanted a faster, better serverless, and WebAssembly enabled that. And that's really because of WebAssembly's origins, that web word. So WebAssembly was made for the browser, which gave it these unique characteristics. They're very small bytecode packages, so a .wasm file could be around 250 kilobytes. Beyond that, they're portable, so because the browser has to run across operating systems and architectures, so does WebAssembly. You only have to compile it once, and it runs anywhere. Beyond that, they start up instantly, like Sudesh mentioned, so you have those sub-millisecond starts because we don't want to wait for someone to blink 4 times for our page to load. And then finally, and most importantly, because browsers run a ton of untrusted code next to each other, that code needs to be isolated from each other. And so WebAssembly comes with a sandbox security model. So you load it into linear memory, and it has no access to host resources unless explicitly granted access. And that's a key tenet of serverless. It's the fact that you have multiple tenants running on the same piece of hardware, and they need to be isolated from each other. So how do I get started with this? WebAssembly may be daunting or new, and several years ago we created Spin, an open source CLI and WebAssembly runtime that's a CNCF sandbox project to get you started with it faster. So you simply download Spin, and what comes with it is SDKs, templates to get you started, multiple triggers, and a local developer experience, along with multiple deployment and hosting mechanisms. So in diagram format, what that experience looks like is you download the CLI, and now you do a spin new. You say, what templated application do you want? So you could do HTTP triggered Go applications, REST applications, Python, JavaScript. WebAssembly is polyglot. Then you can do a spin build, and now you didn't need to know how to target WebAssembly from your native language toolchain. We abstracted that away from you. With a spin up, you're running it locally, and then this is the important decision now. You decide where are you going to deploy this. And so we're talking mainly about the lower one here, where you do a spin Akka deploy by downloading the Akka plugin, and now you're deploying it globally across Akamai's network to 24 regions where it can be instantly accessed by the nearest user. Another option, if you're familiar with Kubernetes and want to self-host, we have the open source project called SpinKube that enables running WebAssembly directly on Kubernetes nodes using a shim. So I want to quickly look at that experience through a quick demo, just to show you how fast this is. So we did a spin new here. We're at KubeCon, so I'm using Go as our templated application. We're deciding it's going to be triggered by HTTP. I now have this application scaffolded for me locally. And you can see when we look at the scaffolded function, it's just a simple hello world, receives an HTTP request, returns a hello world response. I'm doing a spin build. We can see here that we get this main.wasm outputted. I do a spin up. It's running locally. I can test my APIs where they are. And then I can hit that endpoint and get my hello world response locally. So now that I'm done testing it locally and making sure it works as I expect, now I can do my deployment. We talked about those two options. Fermyon Wasm functions is going to be on the top, and then the bottom is going to be SpinKube. So above, I just did a spin Akka deploy, and that's it. After logging in, now it's being distributed across the network. Below, I actually provisioned a K3D cluster locally, and so now I'm pushing my WebAssembly function as an OCI artifact. So it's not just containers that can be OCI artifacts, other bytecodes can be as well. So we're pushing that to a registry. Here I'm using ttl.sh, which I always love shouting out. It's a very cool open source ephemeral registry. And then now I use a new plugin, the Kube plugin, to scaffold up a spin app custom resource and apply it to my cluster. The spin operator automatically put a service in front of it. I'm port forwarding that locally to test it, and then just hitting that endpoint and getting another hello world response. And under the hood, you'll see that these are pods, is what it looks like on your cluster. These are really instances that are being executed by a custom shim. Above, our deployment completed. It's available across 24 regions. We can hit that global endpoint. Anyone in this room could hit that. And hello world. So that's kind of those two options that we discussed. And now we're going to transition into some production use cases that we're excited about. And the overall strategy here is that we're not only putting the function closer to you and making function execution faster, we're also coupling the data that's relatively static with the function itself. So we're embedding data into the function so that lookups don't have to make extra API calls. So Sudesh is going to go a bit more into that.
If containers boot fast, Wasm teleports. In edge computing, the fastest query is the one you never send. For Kubernetes engineers, think of this as snapshotting your pod after the init containers have finished, so every new instance starts ready to serve. Wiser does that for Wasm components, which means predictable startup and consistent data state anywhere in the world. Traditional functions spend time fetching data, a redirect list, a GeoIP, or a pricing table, every time they start up. Instead, we compile those static or semi-static data sets directly into Wasm binaries. That tool that makes that possible is Wiser, as Kate said. When it spins up on the edge, it already has the lookup tables in memory, so there's no network call, no cold start, no lag. All of these examples are simple, but they're building blocks of almost every latency-sensitive system.
So I'm going to jump into one of those examples that Sudesh mentioned, which is high-performance redirects. And to do that, we're just going to go straight into the editor. So the idea here is that I have a site that's has some temporary redirects. In this example, you can imagine that I am a garden retailer and I have some pots, and I decided to rename them. We're no longer the Biodome pot, we're the TerraCore pot. And what this means is that I need to go from these previous paths to these new targets. And so this is an out-of-the-box solution that we created for customers to do large-scale instant redirects. And actually, I just want to do an overview of some of the functionality of it. I got a little excited to jump to the code. But what this does is we built this function. It's open source. You can check it out at Fermyon Wasm functions examples and actually deploy it immediately. But it has O of 1 lookup times because we've abstracted, instead of having one large map of hundreds of thousands of redirects, we flattened it into 2 data structures that we pre-initialize in that function with Wiser. And we are using Wiser there, and we can actually scale up to, we've seen 1 million redirects with O of 1 lookup times and sub-millisecond executions here. And that's just by using all the WebAssembly tooling we have out there in our best interest. And we also use REST here to be hyper-fast as well. So going back to our TerraCore change, as a user of this redirect function, if I want to deploy it, the first step is what are my redirects? And you can see here I have around 200,000 or around 100,000 redirects in this file. This is a spin app directory that I have here. You can see that I have my spin.toml, which defines the application, and my source code. I'm going to go ahead and do a spin build. And while that's building, I'll show you, well, that was really fast. I'll show you what we did there. And here we actually have a bit more complicated of a build. We're pointing to a build script that we'll look at in a second, and we're passing in 2 maps of data, the sources paths and the destination paths. And then we're setting what is the default status code for redirects. There are 2 status codes that you experience when you do redirects. 301 would be permanently moved, so say you're doing a website migration. A 302 would be a temporarily moved. And when you send that back to the browser with a location header, it basically tells you where do I go next. And so that's what our function's going to do. The build script does what we talked about earlier. We build WebAssembly targeting, we build our Rust application targeting WebAssembly, and then we use Wiser. Here's where we're using Wiser, which you can download, and we're passing in those 2 maps and pre-initializing that function and snapshotting the memory state. And then there's other WebAssembly tools out there beyond Wiser. There's Wasm, which basically does dead code elimination to make your component even smaller. And then what the result is with 100,000 redirects, our WebAssembly component is 2.2 megabytes. 1 million redirects, it's about 19 megabytes. Let's go ahead, and now that we built it, I'm actually going to just do a spin deploy. A spin Akka deploy. And I've already deployed this function globally, so now we're seeing this as a version update. So you can continually, in your CI/CD pipelines, update the versions. And so I'm going to go ahead and deploy this. While that's deploying, let's look at how Wiser pre-initializes. You can see here in my Rust code, I have this init function. This tells Wiser, this is what I want you to execute, and then snapshot the memory after. It's very simple. It's just loading in that sources file and targets file and setting them in constants under the sources constant and the targets constant. And then for each execution that comes in, similar to our hello world example, we just look at the path of the incoming request, we look it up in the sources map, and then we look up the destination and the targets map, and we just change the location header to have the target. So we've deployed this globally, and I'm gonna go ahead and give it a quick curl. This should redirect to about TerraCore. And you'll see here that we got that 302 moved temporarily, and it's saying, okay, browser, go to about TerraCore instead. This is a box on my desk in Seattle, which has better Wi-Fi than where we are. A little homage to KubeCon EU that just happened. We can do the same from Paris, a Paris box, and we can actually go ahead and do a load test of this. And you'll see I just did 10,000 redirects, 125 concurrent requesters, an average of 13 milliseconds to go through a global load balancer, be directed to the nearest instance, execute that function, and come back. And so now we can go back and just kind of look at how that execution path. So we executed that. We went to the application load balancer, that global traffic manager. That was routed to the nearest edge region. We executed our function, and then the response returned to the user. And depending on the physics of where you are, that ranges. A follow-up question we get from people is, how do I integrate this with CI/CD? This is relatively static data. Obviously, redirects change. You add redirects, you remove redirects. What does that look like? You could make it so that your GitHub workflow, for example, watches that redirects.txt file every hour, every day. However often that updates, you just redeploy that function, and it distributes globally in about 1.5 minutes. With that, I'll pass it off to Sudesh to talk about some other cases.
If it runs fast in one region, imagine how it runs everywhere else. What Kate demoed is one example of a pattern we can apply near anywhere latency matters. These are new micro workloads. You can define them declaratively, deploy via SpinKube, and then run globally across 20+ regions with sub-millisecond cold start times. Same DevOps discipline, just expanded. Now, a couple of other examples that I have up here are mirroring traffic streams, where you can replicate live data at the edge for observability or replay without backhauling. You could do AI workloads, everything from LLM integrations to RAG pipelines pushed closer to users or devices. And as you're thinking about the things that we actually deal with sometimes at Akamai, hyper-personalization, which is edge logic that rewrites or paints pages based on user context or crawler type. Data transformation also kind of falls into that bucket. Normalize or filter streams before they ever touch your core systems. Think of an IoT use case there. And traffic filtering and proxying, even A/B testing, classic edge compute use cases also fall great into sort of the way we see this being deployed. All of these benefit from the same principle: bring the logic to the user, not the other way around. All right. All right. Well, everyone demands an AI use case, so here it is, y'all. We're doing AI inference, what Kubernetes did for containers, orchestrating intelligence everywhere. For Kubernetes developers, this architecture feels familiar. You've got your cluster in the core running LKE, and now through Fermyon Wasm functions, you effectively extend their cluster globally. Think of this as a federated inference. Your CRDs just don't deploy to nodes, they deploy to the edge POPs for this scenario. Starting at the top left, the user application hits an AI endpoint, DNS, UI, or an AI API. That request is first handled by the Akamai Edge, where we provide security, caching, and load balancing. The distributed layer in step 3 is powered by Fermyon Wasm functions, where inference can execute closer to the user. And this is where real-time responses actually impact that user experience. Step 4, for heavier workloads, full execution can happen at GPU, training, and traffic routes back to Akamai core regions, where LKE orchestrates what's needed for those pipelines. In step 5, developers then continue analyzing from the core, but the live latency critical execution happens at the edge. So this is a full stack AI fabric, inference near the user, orchestration in the core, one continuous data plane, and you can use any model you want. Edge and core don't compete here, they collaborate, and that's sort of the big change that we're talking about. Now, One of the things I get to do in my role is work with customers to deploy Fermyon Wasm functions. So I want to give you a couple of real-life examples that we've already kind of deployed. The first is, think of these as event-driven micro-functions. They're deployed like CRDs, triggered by traffic and run in under a millisecond. The platform handles scheduling and observability, and you focus on the function logic. In that first example, retail sites often rely on legacy CMS systems where modern AI tools can't parse or classify content. By running a Fermyon Wasm function at the edge, we can scan and tag page content in real time. Sometimes we also use this for detecting product attributes, color, or sentiment. This means smarter recommendations, faster merchandising, and better search indexing without rewriting the code that's underneath. Now, in the second example, real-time page repainting for travel providers, this is about personalization. The same page can render differently depending on who's looking at it. For example, a human visitor sees an optimized UX, whereas an LLM crawler sees a context-rich summary. Those transformations happen instantly via Wasm functions on the edge, no round trip, no origin, no performance trade-offs. These are some resources that you can access that have the code samples that Kate showed. They also have some links to some of the Akamai resources if you want to see how those things are deployed. And we also have sort of the links to the community on the next slide. And then we want to thank you today for attending the session. We do enjoy feedback on how to improve and make this useful for you guys. It's always difficult to squeeze this much content into this much time. And we want to leave you with this quote: from milliseconds to microseconds, we're not just delivering content anymore, we're delivering cognition. Thank you so much.
Thank you.
Oh.
What Wasm runtime do you use?
Yeah.
And when you talked about snapshotting, how do you deal with version dependencies of runtime on the compiled version? And third question, do you not use AOT compiled binary code?
Okay. So for the first question, it was what runtime do we use? So Spin is both the CLI and the runtime, but if you're familiar with WebAssembly and curious about what WebAssembly runtime's under the hood that Spin's utilizing, it's Wasm time, which is a Bytecode Alliance runtime. The second question was about the snapshotting. How do I manage the versions of it? So I don't think I fully understand that one, but are you talking about with deployments or?
With Wasm time, we know there's a version change that happens,
Oh, yes.
and there's a dependency of the compiled version to work only with that version. And every release is sort of a major version, at least today. So.
Okay, yeah, so how do we handle WebAssembly or Wasm time runtime updates, and is my WebAssembly component always compatible as those upgrades and updates happen? So Spin, we try to make that easy for you, and so any Spin component, so say you built on Spin 3.4, we just had a release of 3.5, you can run that 3.4 component, we handle that for you, and make sure we get the latest and greatest of the Wasm time and WASI standards, so we right now in 3.5, we actually have access to WASI P3 interfaces, and we have those available, but you also can still use the P2 interfaces. So we basically abstract that away from you and make it so that the runtime can handle. And that's actually the WASI ecosystem does that too. So there's a standard of you have to have backwards compatibility on your interfaces. You had a third question. Can you remind me of that one as well? Thank you. Okay, so for ahead of time versus real time execution of the functions depends on what language you're using. So for Rust, everything's ahead of time compiled. Interpreted languages like JavaScript, we actually compile the interpreter into the Wasm component and it executes with it. So that's kind of how that's handled with the language ecosystems. It differs.
So with the JavaScript, do you find that the Wasm binary becomes much larger because you're building in the runtime? Oh.
Yes, it's bigger, yeah. Great. We'll both be around. Both Akamai and Fermyon have booths in the expo hall. We'll also be here today, and then WasmCon is later today where we'll be as well. So feel free to find us, ask questions, and these slides are already uploaded if you want to access some of those resources. So thanks for all your time.
Thank you.